we'll get to the topic at hand, in particular computer vision with YOLO, which stands for You Only Look Once. So I'm by no means an expert on computer vision, but I've had a little bit of experience back in the day, and the typical computer vision model was basically this pipeline of operations where you take an input image, you do a series of image processing with the expectation of getting features, like lines if you will, and then those groups of lines you'd feed into an object classifier, which hopefully would spit out objects. So, kind of going through that phase, you probably decode the frame and then a sequence of image processing. You may change the color space, from color to grayscale. You may do some blurring effects in order to remove high frequency noise. You may do some thresholding on the pixel intensity or color, and maybe do edge detection. And then oftentimes you just have these pixels that are disjoint, but they should be connected. So you do these things like convolution, where you basically grow connectivity and then proceed to shrink it. But the point is that this image processing, you would go through the frame pretty much for each step, right? Pixel-wide operations. And the trouble with that is that's incredibly CPU intensive. It can be memory intensive. But that was kind of like the traditional model. Or at least what I knew of computer vision when I took it some decades ago. YOLO was introduced by Joseph Redman, and the two significant things that kind of come out of that is, first off, he eliminated the idea of separating a detector which fed a classifier, and instead the idea is the classifier is the detector. So the way that that's actually handled is you take an image and you subsample it into a series of regions. And then the assumption is that you have an object in each one of those subregions. So you run a classifier through it. And in this particular example, we've got 8 sub-regions that have a dog in it. So imagine you would run a classifier in the entire all the subregions, and in those 8 you would find some part of a dog. So the classifier would report, I've got a dog in this subregion. So then you basically take those 8 regions and merge them all together so that you have basically the bounding box that surrounds the dog. And that's precisely what YOLO does, is it basically just breaks down the image into subregions, runs classifiers, merges the results, and hopefully what you have in the end is a series of objects that you can draw a line around, where their location is and how big they are. So the end result on the image on the right is basically an example of running YOLO. You have a dog, you have a bicycle, and you have a truck. So that's kind of the idea, and the term YOLO actually calls for you only look once. So the other key thing that YOLO has is the intent that you actually evaluate a pixel one time, as opposed to the traditional model where you go through the image repeatedly to try to extract the significant components of it. So that was the two key things about YOLO has to offer. We're going to get into briefly how to set up and configure it, but there are at least 2 technologies that we're going to be making reference to that I wanted to at least let you know what they are. So darknet, we'll be making references to those in the following slide, and it's not the dark web and it's nothing nasty. It's basically the open source neural net that's implemented in C, so it's incredibly efficient. It has CUDA extension, so it allows it to run with GPU and CPU acceleration, but that is basically the framework that YOLO was actually built upon. The other thing that some of you may already know is we'll make reference to COCO. So that's it stands for Common Objects in Context, and all that is a great big data set specific for computer vision projects. So it's got over 127,000 images, of which 880,000 instances where they take the form of what's on the slide. On the left is the example image where you have 3 key objects. You got a person, you got a dog, and you got a frisbee. And then the data set, people meticulously identify these objects and basically draw a silhouette around them. And the intent now is when you have that and you classify this, you say this is a person, this is a dog, and this is a frisbee, you can use this for your computer vision as training. So this is what a person may look like, and imagine doing this for 127,000 images that have people. You get a pretty good representation of what people would look like in a variety of lighting and everything else. So that's COCO, and we'll make reference to it a little bit later, but that's the significance of that. So COCO in particular is the data set that YOLO is pre-configured and customly is trained on. Just out of the box, it's trained on the COCO data set. You can do a custom training of YOLO, so you can start from scratch with your very own data set. If you want to specialize it in, detection of objects that aren't covered or something specific. But out of the box, COCO has been has these objects basically defined. So when YOLO is trained on COCO, it should be able to detect these 80 types of objects. So it's kind of the significance of COCO in particular, and this is the kind of things that the next examples should be able to detect is kind of the point. In terms of setup, most of my machines are Unix. I've been using Ubuntu. In particular, these slides I did for 1604. I have no reason to believe that it doesn't work for later versions, but this was a primary sequence of events in order to get it installed and configured for me. You will notice that this is the first time I've had a project that required, Python 3. I haven't found a repeatable sequence to actually execute it with Python 2, but we should probably be moving away from that anyway, hence the question that I asked earlier. We do install this series of, essential modules, if you will. In particular, OpenCV, we'll be using that to actually read in the media files to allow us to actually deliver them to the YOLO detector. And then the last 5 steps are really the YOLO specific stuff. This pip install YOLO 3.4 that's actually the Python interfaces for darknet, okay? And you'll see references to that in just a bit. Then we actually have to have the YOLO NeuroNet configuration, which is comprised of the config file and then the weights. So we're going to go ahead and just go download those and place them in the current directory as well. And then, since it was trained on COCO, we're going to go ahead and download the COCO data set. And the COCO names, which is basically what this list comes from. That isn't really used in our example, but at least for reference, it's kind of good to know what kind of things this thing should be able to detect. And what you should have after that is, after you've executed those steps, is you should have a directory tree that looks something like this, where we have our data subdirectory with the COCO data, and we have the COCO names in there as well. We have the config and the weights, which comprise the YOLO NeuroNet. We'll have a couple of media files, which you can use however you see fit or wherever you get them from, but we have a sample JPEG as well as a video MPEG-4. These are the examples we'll use in the next slide. And then a very brief Python example, which is the next thing that we're going to look at. So our example for an image takes the following form, I guess. Line 1, as you can see, we're using Python 3. Line 3, we're importing from the PyDarknet a detector and an image. The detector is the real significant bit. The image is an input data structure, so we'll be using that as well. Then line 4, OpenCV, we're basically using that just to read in the image, which we'll see in a minute. And then line 6 is where the real significance is. We basically initialize our detector. We specify in our YOLO config and our YOLO weights. And then we also specify the COCO data set as well. So after that, we've basically got a detector that should be capable of processing images and spitting out results. Lines 8, we use OpenCV to read in a JPEG. And then we convert it in line 9 to the darknet raw image type. And that's when in line 11 we basically pass that image into the detector and we retrieve our results. So then down in 13 we basically, the results will be a list of tuples of the form of, cat, score, and bounds. So the cat is basically the category or the classification. It's a dog, it's a cat, it's a bike, it's a person. And then the score is like a confidence level. So imagine that I've detected a cat, but I'm only 1% confident it's actually a cat. Or I've detected a dog and I'm 99% confident it's a dog. So that's how that score is relevant. And then the bounds is where did we find that object in the image. So that particularly will have an X and Y location for the centroid, a width and a height, which we can use in line 15 because now we can basically draw a bounding box around the detection, right? Followed by line 16 where we basically just write out the category or the classification of that object. It's a dog and the like. Last two steps, we go ahead and show the image, and then we wait for a keyboard user to hit a keystroke. And what you should get is something that looks just like that. Input image on the left, classifications on the right. Dog, bicycle, truck. So that's kind of the primary example for doing something for an image. But let's do something a little more interesting and go on with a video. So you can see this is primarily very similar in nature. The only difference is we're basically retrieving images from the video one by one. And rather than display them, we are drawing the rectangles as well as the text. But rather than display them, you notice I'm just actually writing them out to a JPEG results file. And the reason for that is that on the systems that I run on without the GPU acceleration, it takes seconds to process this. So I didn't want to show this in non-real time, real sluggish behavior. So after all the images are done, I basically reassembled them into a video that looks pretty much like this. So you notice that the lighting is pretty poor in some cases. Some of the detections even work with only part of the people in frame, like here. It's detecting persons with just their legs exposed. And you will see that there are some misclassifications because I wasn't paying attention to any of the scores. I was just recording or basically drawing boxes around them regardless of the confidence or the score level. So some of the things come up as dogs or some are misidentified as persons for a little while, but they self-correct. A very busy intersection, you'll see cars. You'll actually see a truck in the upper right even, and that's pretty hard even for a human to identify. Bicycles and people. Got a small Jeep on the left and just with a partial view and it still detects it as a vehicle. Produce stand is identified as a truck, but started life that way probably too. And even when you get to some of the exotic animals like the giraffes, the COCO data set has some of the some exotic animals actually trained in there. So that's an example of a video and an image. Let's just briefly talk about performance. Most of the systems I have at home are just dinosaurs. 8-year-old laptop. It basically took me 30 seconds to process a frame approximately. And that's partially why I reassembled the results into a video. But here's the interesting thing. Regardless of the video quality, whether it's high resolution or incredibly low resolution, it approximately runs at the same rate. So even the 240 by 130 basically runs at 30 seconds. And that completely contradicts the typical, the traditional image-based or image processing-based computer vision, because a lot of the time, remember, if you have to process a high-def image repeatedly, it gets incredibly costly. So one of the first things you do when you take that approach is basically cut it down to as small of a resolution as possible, with the objective of getting something that approaches real time. But obviously, 8-year-old dinosaur versus modern machines, your mileage is going to vary. I wasn't making use of the GPU acceleration, and there are numerous systems, from embedded, Raspberry Pis to mobile phones, and just COT systems that execute in 30 frames per second. So it's actually a very efficient, very fast detection algorithm, and it only gets faster. It originated with YOLO 1, then it went to like a YOLO 5000 or 9000. I'm sorry. The one that the example I just went through is YOLO 3, and there's a 4 and a 5, which only get faster and better classification. And the last thing I thought maybe it'd be worth talking about, or kind of demonstrate the types of things you could use. Obviously, you can do almost anything that your imagination will allow. But one of the things I always questioned was, in lecture halls, one of the things that they generally want is they want a cameraman, right? Who's going to, follow the subject and draw the user's attention. But what if you didn't need that anymore? With the high definition cameras that we have today, if you had a wide enough angle and you could track the subject in the video, why couldn't you auto crop it? And that was the example that I tried to just play with a little bit. The guy on the video and the guy on the camera may resemble one another, but this was something we did about a year ago. And right now all we're doing is every half a second, I'm processing that image, detecting where a person is, and then centering that rectangle on that centroid. And the initial results were really jumpy. So I attempted to actually put a shaper in there to kind of smooth the camera motions, but you can see it's got a lot of possible improvement. That's kind of like the idea that you could use with relatively, dozens of lines of code, and something that you can kind of play with. I think the last thing is, so again, Joseph Redman was the originator of YOLO. His website has references to DarkNet. That was the foundation of the open source neural net that YOLO was based on. He's got documentation for YOLO. You can probably find a number of YouTube references that kind of touch on it. I just included one. The PDF is the original research paper. And then the last bit, because when I stumbled upon this, I had to include Joseph Redman's resume, because where else are you going to ever see a My Little Pony themed resume? Last bit, I've made these slides available at that GitHub repository. I normally have a lot of ramblings about computers and software. I have my own blog. If you're at all interested in subjects like this, feel free to give it a peek. And I go under Lapelt GM on the Slack channel. That is all I really have.